Hello, I'm JW. This is part of a series of videos on diverted neutral current, this being the first part. Now, diverted neutral current is also called neutral current diversion in some places, and there's various other variations of it. But essentially, as the name suggests, what we're talking about is current which would normally be in the neutral conductor going somewhere else. So in other words, diverted through some other path. And what we're talking about here specifically is what happens outside of an installation. So this is not something within individual circuits inside your building or whatever else. This is something which occurs due to problems in the network itself, as in the supply to the property. So not something you're going to find within the building, but it is something definitely to be aware of, because those problems which can occur may lead to unsafe situations either at the supply point or in various other areas. So going to have a look in this video at essentially how these things happen and what the general things to look for will be. And next time we're going to have a look at a demonstration in an actual test rig which I've made, and that will basically show the various things in their sort of a simulated environment. We're going to use a test rig because it's very difficult to show this in the real world, because obviously those faults and things don't generally exist. And the other problem with doing it in the real world is that it's actually fairly dangerous, because 230 volts and so on could be exposed on various parts. So we're going to look at that next time. But to start with, let's have a quick look at what diverted neutral current actually is and where it's likely to occur. Some of the things to actually look for when looking at any installation. Now let's just cover what diverted neutral current actually is. Now, as the name suggests, this is current which would normally be flowing in the neutral conductor, and it's been diverted somewhere else. So in other words, it's not going where you would imagine it to be, and it's called diverted neutral current. Some places you'll see it also called neutral current diversion, and no doubt various other variants of that, but it's all the same thing, just for some reason various different places call it slightly different things. And it's important to realise that this is outside of your electrical installation. So in other words, it's in the supply network, which obviously provides the electricity to your building. Now this is important because we're not dealing about things, say, within the installation or after the distribution board or consumer unit or whatever. This is something which will occur within the supply network itself, possibly coming in from other properties connected to the same supply. So it's not something that we'd normally have anything to do with. And the reason it's being covered here is because problems in the supply network can cause current to flow in places you wouldn't expect, and in certain cases normal operation may cause current to go in places you wouldn't expect either. So forget about what's within the installation, this is going to be before that, but it is important when it comes to disconnecting things like main bonding conductors and the earthing conductor and so on. Now, for the purposes of this video, and in fact almost all the time in the real world, the type of installation we're going to be talking about here is TNCS, mainly because in the UK and certainly most other places that is the most common type of supply. Certainly in the UK, anything in the last 50 odd years is almost certainly going to be a TNCS. And even things which may look like, say, TNS, probably aren't. They're probably TNCS, either being converted deliberately or just purely by changes to the network. You can get neutral current diversion on other types of network, but essentially we're not going to be looking at that here. We're going to be sticking with the most common choice. And just as a reminder, the point about TNCS is that the conductors to your installation, as in what comes in from the street or wherever else, there's only going to be a single conductor for the neutral and the earth. So coming into property, you're going to have a single conductor, which is going to be the combined neutral and earth conductor, or the CNE, and then you're going to have your line conductor, and if it was a three-phase supply you would have obviously three of those. But the important thing here is that the neutral and the earth are combined into a single conductor, and that goes all the way up to the boundary of the property, and that's normally linked together in the service cutout. And this is essentially what the C in TNCS means. It means these are combined rather than being separated throughout. They are separated within the installation, so you would have your individual neutral and earth conductors there, but combined outside. Now here we have a couple of installations. We're assuming these are two adjacent properties in the same street, and we've got our single phase supply coming in from a common supply cable out in the street. So our line comes in, and then our combined neutral and earth conductor comes in. That is split in the property into the separate neutral and earth terminals, and exactly the same in the property next door. So line neutral and earth there, but the neutral and earth, of course, are shared when it comes into the property, separated once they're inside, hence it's TNC for combined and then S for separated. And we'll assume that these are adjacent properties, so we'll put a division down the middle. Now in this particular configuration there's no possibility of any diverting neutral current because there's literally just the electrical supply coming in. If something unfortunate happened to this, such as the C&E conductor was broken and busted open, pretty obviously nothing in this installation is going to work anymore, but there's no way the current can actually go anywhere else simply because this conductor is broken and it's not connected to anything else. So what's going to happen? All of the metal work and the installation connected to the earth terminal is going to become live at 230 volts. We've covered that in a previous video, but again nothing's going to happen. Of course, if someone grabs hold of that and they happen to be standing outside rubbing a garden tap or something, they're going to get an electric shock there. But in terms of current flowing anywhere, simply not going to happen because we don't have a complete circuit for the current to go. However, this isn't particularly realistic because most buildings will have other items, and by other items we're talking about conductive items which come in from outside, or in other words extraneous conductive parts. And this could be things like a water pipe or a gas supply or even a metal frame building, say an industrial unit or something divided up into say 4 units, and it's a metal frame building. And of course all those metal parts will come in and they will have to be bonded to the main earthing terminal simply because of the fact they are extraneous and are bringing in a potential from outside, in this case about pipe buried underground. So you would have your main earthing terminal and you would have a connection going over to that particular water pipe in both properties. And if they're water parts like gas, water, or whatever, you'd have that going to all of them. Again, pretty standard stuff, nothing really unusual here. And these pipes need to be bonded simply because they are at earth potential coming into the property, and you want to make sure that they and the main earthing terminal are kept at or as near as possible to the same voltage. That's why they're called equipotential bonding. Equipotential meaning equal potential or equal voltage, and that's basically what it's for. It keeps those two at the same voltage so you don't get a shock if you're in contact with both of them. Now of course water pipes, things don't go back to some kind of central place. Just as with electricity, there's going to be some kind of common pipe or whatever else going along in the road, and you're just going to have little bits coming off going to each property. So as well as being buried in the ground itself, they're going to be linked together, meaning that all of the pipes in all of the houses all the way down the street are all linked together, and if they're made of metal, you've now got an electrical path through to all of the properties. Now the first type of neutral current diversion is something which will happen pretty much by default in normal operation, and this is simply because you've got now 2 paths for current to return. So let's say in this particular installation we had say 10 amps coming in here on the line, bearing in mind it's AC so it's theoretically in both directions, but we'll assume it goes in and out here because that's just a bit easier. So 10 amps on the line conductor, and you would expect that there should be around say 10 amps on the neutral or the combined neutral and earth as well, because of course the current is going to be the same on both. And if we've just had these 2 conductors, that would in fact be true, but there's actually a problem here because we've got this bonding conductor going over to our nice solid chunk of copper here, gas pipe or whatever else, and that happens to be connected not only into the ground itself, it's also connected over there. So we're not going to be getting 10 amps here, we're going to be getting somewhat less than 10 amps there. Say it might be say 6 amps for example. The other 4 amps is going to go along here, and it's going to go down through the pipe here, and it's going to go into the ground, and some of that will just go into the actual ground itself, finding its way back to the transformer, wherever that might be. But a fair chunk of it's going to go along here, and possibly go into your neighbour's property, and through their bonding conductor, and then into their combined neutral and earth conductor, and it all goes back to the same place eventually. And this is inevitable on TNCS systems with main bonding, simply because you've now got 2 parallel paths for the current to return in. It's going to be shared between them depending on the actual resistance of the various components, but you can't avoid this. So if you've turned on some stuff in your house and you put a clamp meter say around the bonding conductor here, you're going to find there is some current there. It's pretty much inevitable, you can't do anything about it. However, this is entirely normal in operation. So this is the kind of diverted neutral current which is going to happen anyway. So if you go to an installation, put a clamp meter around the bonding conductor and find there's current there, it does not mean there's some kind of massive failure occurred and you have to call people and all the rest of it. It could in fact be normal operation of a TNCS supply. Now if you were to turn off this supply and isolate it, there won't be any current here, so you wouldn't expect any current here either. However, there may be current here because if you go to next door, let's say that their supply is actually turned off for whatever reason, you might still see some current here because it's coming from next door, just simply going around there into the combined neutral and earth conductor and back into the supply. It could be, say, the full 4 amps there, it could be, say, sort of 2 amps or something. But again, this is quite normal. Bearing in mind we've only got 2 properties here, you could have a whole row of houses, say 20 of them, multiply this up by 20 with various loads on each one, you will be seeing some current in these bonding conductors. However, the important thing here is that if you were to disconnect this here after isolating your supply, first of all there's going to be no current there because obviously you've broken the circuit. But the key at this point here is what's the voltage going to be there? And the answer of course is going to be pretty much nothing. This is still going to be at the same potential as the incoming neutral, which it should be at or very near to the earth potential. This again will be earth potential because first of all it's buried in the ground and it's also connected back to this exact same terminal next door, down the street, up the road, who knows where else. So although there was current there, once you've removed it, you're going to find that there's no actual voltage here, or it's going to be incredibly small, certainly in the region of less than 1 volt. This represents normal operation, pretty much what you're going to find in any property with a TNCS supply. Now let's look at a situation where something has gone horribly wrong in the supply network, and this is what's going to happen if things get turned off or conductors become disconnected. Now to make this reasonably simple, we're going to look at the situation of 2 properties and we're going to assume that there's no other connections to anywhere else via the metal pipes or whatever else we've got. It is literally just those 2 sharing a single shared metallic part, like a pipe or whatever else. Now again, normal operation, nothing's going to be going wrong here. We've got our 2 supplies, current coming in here, coming out of here, and likewise over there. Inevitably some current is going to go via the shared metal pipe because eventually it's a parallel path to both the supplies, but as we saw previously, that's pretty much normal and expected. But what happens when this conductor here gets busted, either due to someone damaging it or more likely some 50-year-old connection out in the road corrodes away and disintegrates? What's actually going to be happening now? Now previously, when that connection was broken, everything in the installation simply stopped working because of course there was no path for the current to flow through. The circuit's broken, so of course nothing works. And we also saw that this part here, the earth terminal and the neutral, basically goes up to around 230 volts because it's basically the end of a circuit just open there. However, in this case, everything in this installation is going to carry on working just fine. And the reason is that, say we had our 10 amps coming in here like we had earlier, the 10 amps now is going to be going here. Can't be going here because obviously this is an open conductor. Bearing in mind this will be outside in the street underground where nobody would have seen it. So 10 amps going there, 10 amps going via our bonding conductor, 10 amps going via our water pipe. Some of that may end up going into the ground itself via the fact that it's just buried in the ground, but the vast bulk of it is going to go along the copper into next door, and you're going to have 10 amps here and obviously also 10 amps there going back to the C&E conductor. Now the effect of this is that this property, everything is working as normal, no one would even suspect anything was wrong. Likewise over here, if this was turned on, nothing is going to happen there either. And if this particular property, say, had an 8 amp load switched on, then of course you'd also have the 8 amps going here, so you'd have probably around 18 amps there, as you're now having the current here from both the property there and of course the property here, with the bulk of it going via the conductor effectively as the water pipe. Some is going to leak away into the ground, And if you had other properties, this becomes far more complex, but a lot of current flowing here that basically shouldn't be. Now let's just say you want to go and work in the property here on the right side, and you want to just disconnect the supply here, undo the bonding or whatever, make some alterations, do all of that. So the first thing you would do is to disconnect the supply here. So that would eventually remove the current there, and then you would obviously remove the 8 amps here as well. Completely isolated, everything's turned off, and you go to check if there's any current in this part here, and you see there's about 10 amps going through. Now, is this a problem? And here's where the real problem is, in that you can't tell where this current's coming from. It might be coming from next door in case of some faulty part, or it could be just earlier that we saw that because you've got parallel paths, you're going to have some sort of current there anyhow. But generally, the larger this current is, the more likely it is that something has gone horribly wrong, and in this case, it's effectively the whole load current of that piece over there. Now, if you were to disconnect this bonding here from the earthing terminal, what is going to be the voltage here? Previously we said it was about 0 because it's all connected together, but it's not going to be 0 this time. First of all, by disconnecting this, we've now broken the circuit which was providing the neutral path for the property next door. So this property suddenly isn't going to be working anymore, but of course you wouldn't know this because you're in the property next door. All that happens here is the people there suddenly find that their electricity isn't working anymore. This thing here is going to have some kind of voltage on it, and it could easily be at a dangerous level. If this pipe was not in direct contact with the ground, say it just went through the wall into next door, or it was a part of a building, this could easily be at 230 volts relative to the conductor over here. So if you disconnected this and there was 10 amps between there, you're going to have a large spark going across here when you undo it. If this happened to be a gas pipe and you're working on the gas meter, then there's going to be a chance of igniting any stray gas there. So that is why gas people have those like sort of jump lead type affairs where you can clip onto the two sides before disconnecting it. Bearing in mind that can happen in normal operation as well. However, if you were then to touch the end of this standing on the ground, you can get an electric shock from this or from the pipe itself. While it's connected, that's not a problem because again it's connected solidly through with the copper there. It's all going to be at or around the same voltage or potential. Once it's disconnected, not anymore, you're going to have a significant voltage here, say anything up to the 230 in this scenario. If this is buried in the actual ground outside, this is going to be somewhat less, because some of that current is going to be going away into the ground here. Needless to say, it's not going to be 0, so you might find, say, there was 100 volts there or something. All depends on the exact circumstances, and of course you won't know these circumstances because you can't see next door's gone off and you can't see the property up the street has got a problem and all the rest of it. And again, the total voltage here depends on what loads are switched on in this property, and if it was involving a whole line of properties and there was problems affecting more than one of them, it's going to be the loads on all of those combined together. In this case, we're just assuming the current there is 10 amps and it goes through and comes back here, but of course in reality this is going to be connected to dozens of properties in the street, many different loads coming in here, current's going to be flowing here and all over the place, not even necessarily in the same direction. So the main point here is if you've found current on a bonding conductor, when you disconnect it you may find that there's no voltage at the end of it, in which case it's normal operation, or if there is a voltage here, something is wrong somewhere else down the street or across the road or wherever else, and you can have a dangerous voltage at this point. So some current on the main bonding conductors could very well be normal operation, so it's pretty much inevitable because you've got parallel paths there for the return current from the installation. So just finding some current on a bonding conductor really doesn't mean anything on its own. However, it could mean that there is a problem within the supply network somewhere. You're not going to know where exactly, and it's really what happens when that is disconnected that becomes the major problem. The other possibility is you've got an open combined neutral and earth conductor, and that's going to be out in the street or wherever, so you're not going to be able to see it. Both of these cases you're going to get current flowing via other paths other than the incoming cable, so via bonding and whatever else. So if you're going to go to an installation and disconnect the bonding, first of all you need to turn off that particular installation completely. Of course that's just standard procedure. You don't want to be disconnecting these things when the installation is on, because you're removing a safety feature. Before disconnecting, use a clamp meter on the bonding conductors and any others that you've got there, just to see if there is any current there. If there is any current there, what sort of level are we talking about? We're talking about half an amp or 20 amps or 50 amps or whatever else. Generally, the higher it is, the more likely it is going to be some kind of problem. If there is any current there, when you've disconnected that conductor or other parts of things connected to the main earthing terminal, is there any voltage on the end of it? And you need to check this with a voltage indicator, preferably a single pole device with a contacted metal end, because bearing in mind using a 2-pole thing here, what's the other pole going to go on to? You can't really just stick it on the main earthing terminal in the installation, because that could actually be where the problem is. So, single pole voltage indicator, is there any voltage there? If there is, then this of course is a huge problem. Dangerous situation has been revealed. What that probably means is that some load which was current flowing through that conductor you've disconnected, maybe next door or across the road or wherever, you've just disconnected that, someone else's stuff isn't going to be working. And again, this really comes back to how large was the current you measured before. If it was, say, a few amps or so, could be normal use. If you went to a property, say, and you found that there was sort of 80 amps going through a conductor, disconnecting it would be a very bad idea. There's going to be a significant risk of a huge spark there, or even arc flash coming out of that. Hence the reason to use the clamp meter first to get some idea of what's going on. Now, important to realise that open CNE conductors are not particularly common. There are many hundreds of these reported every year in the UK, but bearing in mind that there's tens of millions of properties in the UK, so a few hundred reports does not mean that every time you go to someone's house you're going to find this, or every time you go to some factory or whatever, this is going to be happening. However, be aware of these things, because these things do occur, and they are being reported. And unfortunately, as electricity networks generally get older, particularly those ones put in the 1970s and 80s and whatever, deterioration, of course, is inevitable, and these problems are going to show up. So the key points here are earthing and bonding conductors not necessarily safe. Maybe a temptation to think, oh, it's the earth conductor, no danger there, but could be various currents and possible voltages if you've disconnected them. Before disconnecting, use a clamp meter. Is there any current flowing in that conductor, whether it's the bonding conductor, earthing, or whatever else? And if you've got multiple bonding conductors, check all of them. If there isn't, absolutely fine, just carry on. But of course, if there is current here, how much? Now, there's no specific limit as to what you might find here. Bearing in mind it could be normal current just going through there because you've got parallel paths involved, but generally the higher it is, the more dangerous this is going to be. And then if you are going to disconnect those, check at the end of it to see if there's any voltage on the thing you've disconnected, and also the other parts as well. So if you have a main earth terminal, you've disconnected a bonding conductor, check that bonding conductor and check the main earthing terminal again for any kind of voltage there, because there could be dangerous voltage appearing there just for the fact you've disconnected it. If there was, and you found there was a significant voltage there, like 60, 80, 100 volts or something, that would be the time to put it back in and then call somebody to actually investigate the network itself, because clearly there is something wrong. If there is no voltage, what you disconnected was just a bit of parallel path current, normal operation, and that's going to be most of the time, bearing in mind that most installations do not have broken CNE conductors. Now that is all we're going to look at this time. Next time we're going to have a look at this in an actual demonstration. I have this test facility which I've made, which we'll have a look at, and we'll actually go through all this again and a few other scenarios as well, just to give an indication of what sort of things you might really see on an actual installation. And the benefit of this testing device is that it does not use 230 volts, it actually runs on 12, meaning we could demonstrate things there which you wouldn't normally be able to do, and also things, of course, it's perfectly safe running on 12 volts rather than 230. However, we'll look at that next time, so until then, thanks for watching.